Good morning, everyone. Thank you so much for joining us for this session, Why Silica Fume Concrete for Full Depth Bridge Decks. This is Justin Rice, president of ACEC Arizona, and it is my honor to introduce this pre-recorded session. Now, what you will be hearing is at the beginning of the video, you'll start to hear an introduction by one of our speakers that wasn't able to make it today. No worries whatsoever, because I have Nye McCarty right here with me to live. So if we have a little time, we can go to some live Q&A. But just to make sure you're familiar with Nye, I'd like to read just a brief introduction. Nye McCarty is the Regional Materials Engineer for ADOT in Flagstaff, Arizona. Go Flag. Is a registered professional engineer in Arizona and received his degree in civil engineering from Arizona State University. Go Devils. Thank you so much for joining us today. And without further ado, we will begin the presentation now.
Hi, everyone. My name is Rosemary Cvijanovic. I am a proud alumni of Arizona State University, where I completed my Bachelor of Science degree in civil engineering and began working with the Arizona Department of Transportation in their bridge department in 2015. So today I will be discussing silica fume and why silica fume concrete for full depth bridge decks. I will be going over the introduction and the project description, what is silica fume, why it's useful, and then my partner Nye will evaluate its characteristics in terms of, workability, compressive strength, rapid chloride permeability, and the air void systems. So one of the primary sources of bridge deterioration is the corrosion of reinforcing steel in the concrete bridge decks. And this is especially problematic in the northern regions of Arizona, where there's heavy use of de-icing salts and chemicals in the winter. So Arizona has been, fortunate enough to have bridge deck construction methods that have been proven to be successful in terms of corrosion protection and ride quality for over many years. However, continued innovations in concrete materials in construction have provided alternatives that are economically comparable to current deck construction methods. And, it can provide improved performance and reduced construction time. One of these alternatives is the construction of full depth silica fume bridge decks. And the primary focus on silica fume concrete has been as bridge deck overlay materials. However, several states have done work in the placement of full depth bridge decks using silica fume concrete that have yielded promising results. So in an effort to provide the best and most economical bridge decks possible in Arizona, a study was developed to evaluate the full depth construction and use of silica fume concrete in bridge decks on Virgin River number 4 in northwestern Arizona on I-15. So Interstate 15 connects Las Vegas, Nevada with Salt Lake City, Utah by cutting across the far northwest corner of Arizona. There are 13 bridges along this route in Arizona that were constructed in the late 1960s and early 70s that are showing signs of age by requiring constant maintenance of the decks. And I-15 is a major truck route with truck traffic accounting for approximately 24% of vehicles. Because of its location, construction can become quite difficult in this area, and this is especially true back when the bridges were first being built in the 60s and 70s. The I-15 enters the Virgin River Gorge, and it first passes through what they call the Narrows. And here the gorge features, limestone cliffs that are as high as 500 feet above the highway. And construction through the gorge is low and that much more difficult. So to help quicken the construction, the state of Utah actually loaned a portion of their federal highway funds to Arizona. And even though the highway is of little importance to the transportation needs of Arizona, since it does not link any Arizona communities, it does serve as a vital link between Salt Lake City and Las Vegas and Los Angeles to the southwest. But despite the extra funding, challenges still remained. Flash flooding and quicksand in the gorge repeatedly caused problems. So to help navigate the gorge's rugged terrain, a special piece of equipment called a swamp buggy had to be brought in from Texas. And the Virgin River is considered the most expensive rural freeway in the country per mile. So Virgin River number 4 is a two-span steel plate girder bridge that crosses the Virgin River Gorge at milepost 14.30. The original bridge was constructed in 1972, and it is a continuous bridge with both spans equaling 132 feet and an overall bridge length of 270 feet. Abutment 1 has a fixed support with a steel rocker bearing, and Pier 1 and Abutment 2 are expansion supports. The web of the girder is 5 feet deep, and the cross section of the bridge consists of 8 girders spaced at 8'7" with 4'7" overhangs and an overall width of 69 feet 3 inches. The concrete deck was 7.5 inches thick with a 1.5 inch clear cover at the top and 1 inch clear cover at the bottom. So the existing bridge was analyzed based on the 2012 LRFD bridge design specifications using HL93 live load. And major findings from the bridge inspection report included extensive transverse and map cracking on the deck top. The deck underside exhibited transverse cracking with efflorescence, deep spalling, and exposed reinforcing bars. The girders experienced crack welds, missing and loose bolts randomly at various locations. So the condition ratings that were given were 5 for the deck, 6 for the superstructure, and 7 for the substructure. 4 possible repair options with associated cost were analyzed for further study. Option 1 was to perform the minimum amount of work by only replacing the bridge deck, expansion joints, barriers, and approach slabs. Option 2 was to rehabilitate the existing structure and substructure to meet current standards while maintaining the existing bridge width. Option 3 was to widen the bridge to the desired standard clear roadway width of 42 inches by replacing the superstructure and rehabilitating the substructure. And then option 4 was to widen the existing bridge as much as possible using the substructure rehabilitation strategy in option 2. So a deck replacement was recommended for Virgin River number 4 due to the severity of damage to the concrete deck and based on previous experience in research analyzing the differences between a deck replacement and microsilica overlay. Since the bridge was previously rehabilitated in 2002 with an MMC overlay, it was not recommended since it did not perform as well as expected. And also a deck replacement would provide a longer service life in the range of 25 to 50 years. The bridge dimensions would stay the same as the existing bridge, except that the deck thickness will increase by 1 inch, making the deck thickness 8.5 inches. An additional consideration was required during design to assess the ability of the existing substructure to accommodate that extra dead load of the additional 1 inch deck thickness. The tasks that were performed was a full deck replacement that would eliminate all the cracking, spalling, delamination, and efflorescence in the entire deck. And this included a new cast-in-place deck, approach slabs, 44-inch F-shaped barriers, new guardrail, and expansion joints. And the bridge also did require repairing the girders, broken welds, bent connection plates, and steel cracks along the diaphragm. So what is silica fume? Well, silica fume is a byproduct from the production of silicone or ferrosilicone alloys. And typically, silica fume contains at least 85% amorphous silicon dioxide, and it's approximately 100 times finer than normal Portland cement. And it's also spherical in shape. So because of its extreme fineness and high silica content, it makes for a highly pozzolanic material. Which means it reacts chemically with the calcium hydroxide to form calcium silicate hydrate, which creates compounds with cementitious properties when exposed to water. So these properties allow the silica fume to refine the pore structure of the cement paste and produce a denser, stronger, less permeable material. The use of silica fume concrete in bridge deck construction has become increasingly popular in the United States since the early 1980s. The primary focus of silica fume concrete has been as a bridge deck overlay material, or also known as microsilica. However, several states have done work in the placement of full depth bridge decks using the silica fume concrete. So it's mainly used to improve the durability, strength, and bonding characteristics of concrete, but it is predominantly used in bridge decks to reduce the permeability of concrete. So significant testing had been done and performed to determine the resistance of silica fume concrete to chloride ion penetration. And it's generally agreed that the silica fume concrete does show a reduction in permeability compared to conventional concretes. And this would be very beneficial to bridge deck construction, as it would greatly reduce the amount of chloride that's allowed to permeate into the concrete and potentially corrode the reinforcing steel. This is especially true in chloride-rich environments such as Virgin River because of the use of all the de-icing salts. Silica fume is added to Portland cement concrete to improve its properties, and particularly its compressive strength, bond strength, and abrasion resistance. And these improvements stem from both the mechanical improvements resulting from the addition of very fine powder to the cement paste mix, as well as from the pozzolanic reactions between the silica fume and the free calcium hydroxide in the paste. So when silica fume is added to the concrete, it initially remains inert. So once the Portland cement and the water in the mix start reacting with each other or hydrating, the chemical reaction produces two chemical compounds, calcium silica hydrate, which is the strength producing crystallization, and then calcium hydroxide. And this is a byproduct, also called free lime, which is responsible for mostly lining available pores with concrete as a filler. So the pozzolanic reaction occurs between silica fume and the calcium hydroxide, producing additional calcium silica hydrate in many of the voids around hydrated cement particles. And this additional calcium silica hydrate then provides the concrete with not only improved compressive, flexural, and bond strength, but also a much denser mix, mostly in areas that would have remained as small voids. There is some concern, however, because the addition of silica fume to concrete does reduce the pH of the pore solution, which could possibly negatively affect the passivation of the reinforcing steel. However, the reduction in pH associated with the amounts of silica fume generally is not that large. So the increase in electrical resistivity and the reduction of permeability to chloride are believed to be more significant than the reduction of pH in the pore solution that could potentially occur. So good practices in placing, finishing, and protecting and curing silica fume concrete include placing the material close to the finishing machine, vibrating to ensure good consolidation, and covering to protect and cure. A pre-placement conference is also beneficial, and this is kind of an opportunity for the contractor to outline all the plans for placing, protecting, finishing, and curing the concrete so everyone involved understands what will occur. And it is also time for the contractor to resolve any unanswered questions regarding the expectations of the owner and the engineer. A key element to discuss is the rate of concrete delivery. A common problem is getting too much concrete on site and having trucks backed up. And then conducting a test placement. So a test placement basically will eliminate surprises. So this gives everyone the opportunity to get the bugs out of the system and to observe and approve all the procedures. The contractor has to commit to having the finishing crew that conducts the trial placement to be the same crew used on the structure. And the test placement is a good time to determine whether any adjustments to the concrete based upon weather or placing conditions will be required. For example, it may be appropriate to use a retarder during high temperatures or a non-chloride accelerator in cold conditions. So it's also an opportunity to try different approaches and different tools for concrete finishing. And the trial placement has to be large enough to allow for realistic finishing techniques to be demonstrated. So at the conclusion of the trial placement, one of two conclusions must be reached. And that's, number one, has an acceptable finishing approach been demonstrated or accepted? And two, do we need an additional trial placement? How does it dry? Well, although silica fume concrete offers many advantages, several factors must be considered before using it. So the addition of silica fume to concrete may increase the early age of cracking because of the very high surface area of silica fume. Water demand becomes quite high, combined with typically very low water contents of silica fume concrete mixtures. And there's little, if any, bleed water. So as the silica fume concrete increases or as the water content decreases, bleeding would be reduced or eliminated. But on the positive side, that means that finishing can start earlier and be completed sooner. So additionally, bleed water will not accumulate under aggregate particles and under horizontal reinforcing bars. There will be no bleed water channels for chlorides or other intrusive materials to use as a shortcut to get into the concrete or reach the reinforcing steel. On the negative side, that makes it much more susceptible to plastic shrinkage cracking. But to prevent from plastic shrinkage cracking, there are a few more commonly used ways of protecting the silica fume concrete from drying too quickly. One method is fogging. So the goal of fogging is to maintain high humidity conditions above the concrete surface during the time from placement to application of curing. And if environmental conditions cause a concern over drying, fogging should begin immediately after the concrete is placed by a finishing machine or after bull floating. And depending upon the type of placement and the degree of finishing required, it may be necessary to fog between finishing passes. Another one is using an evaporation retarder. So you would apply the evaporation retarder after the bull floating is completed, and you do not disturb the product until floating begins. And here it's important to remember that if any type of finishing tool is to run across the surface after the evaporation retarder is applied, the film will be broken and will no longer keep its moisture. So that part is very important. And then the last technique is one-pass finishing, and this basically takes advantage of the lack of bleeding and eliminates the waiting period between placing and finishing. So the overall process is based on two simple concepts. Protect the concrete at all times and don't wait for the concrete to stiffen before applying the final texture and immediate cure.
Thank you, Jojo. So mixtures that include silica fume behave differently when in the plastic state during placement and prior to curing, and also exhibit different properties after completion of curing. These differences pose challenges that must be accounted for, mitigated if necessary, but the overall finished product will be a much more durable concrete. So let's take a closer look at the challenges and properties of the hardened concrete. But first, it's important to point out that some of the general information displayed in this presentation is from studies performed for silica fume bridge decks placed in New York, Ohio, and Minnesota. When we are speaking directly about silica fume mixtures used for ADOT bridge decks, the information will be identified as such. Speaking of ADOT mixtures for bridge decks, a typical bridge deck will have a required strength of 4,500 psi, but the mix is typically designed to achieve 20% above the required strength, or 5,400 psi. We call this the overdesign requirement. Most mixtures, but nearly all mixtures intended for bridge decks, include 20% replacement of the Portland cement with fly ash. Fly ash is a supplementary cementitious material that is pozzolanic and reacts with hydration byproducts created during the hydration of hydraulic Portland cement. It is a very useful byproduct of coal ignition, typically sourced from coal-fired electrical generating facilities. It improves durability, compressive strength, mitigates adverse reactions, most notably alkali silica reaction or ASR, and helps control hydration to mitigate the buildup of heat, which may result in excessive evaporation and plastic shrinkage cracking. It's worth mentioning fly ash because we aren't going to talk about it anymore in this presentation. What we are going to talk about is silica fume. As Jojo mentioned, also a byproduct and like fly ash, a pozzolanic supplementary cementitious material that further enhances the properties of the concrete. Replacing a portion of the Portland cement directly with silica fume will result in a perceived reduction in workability if measured with a slump cone. This is due to the finer silica fume particles increasing the cohesion of the cement paste. However, due to the spherical nature of the silica fume, when energy is mechanically applied to the mix will flow relatively easily at intermediate slump ranges. For reference, the table indicates replacement percentages of up to 25%. ADOT typically requires at least 4% silica fume for bridge deck applications. A small amount of silica fume enhances the properties of the concrete to that which we desire. The water-cement ratios for the data in the chart are relatively high. ADOT limits the water-cement ratio to a maximum of 0.45 for Class S structural concrete. When Jojo discusses the cost of silica fume mixtures relative to Class S concrete, keep in mind we are including only a small percentage of silica fume. Here the reduction in slump is visually represented. Also note that the lower water-cement ratio will reduce slump if not altered chemically. To maintain the same degree of workability as conventional concrete, ACI Committee 234 recommends that the slump of the concrete be increased by about 2 inches above that which would be used for conventional concrete. This increase in slump compensates for the additional cohesiveness of the silica fume concrete. The higher the slump, the easier it is to both perform work with hand tools and close the surface of the concrete during screeding operations. Excessive slump, however, will result in segregation of the mixture where the coarse aggregate sinks while the paste floats to the top, potentially compromising strength and durability. ACI Committee 234 recommends that water-reducing admixtures, plasticizers and/or superplasticizers, be used to achieve the necessary slump without excessively increasing the water-cement ratio. So here you see concrete being placed on the bridge deck with a crane pump and being consolidated with vibration prior to the screed passing over. Looks to be sufficiently workable. The workers appear comfortable. A couple items to note. It's an overcast day. Workers are wearing heavy long-sleeve shirts and some jackets. The concrete is experiencing minimal evaporation. So let's talk briefly about excessive evaporation, plastic shrinkage cracking, and how we try to mitigate these issues if the weather isn't fully cooperative. There are quite a few factors to consider with regard to evaporation. The wind speed, however, is perhaps the most critical. Here we have a reasonably moist and cool condition, but with a wind speed of 8 miles per hour or more, that's the purple line down here with the squares, we have conditions not conducive to silica fume concrete. The evaporation rate, which is the black line with the dots, is well above 0.20 pounds per square foot per hour, even during the overnight hours. Placement of silica fume is very much dependent on cooperation of Mother Nature. If you test her, she'll bite you every time and give you these. That is a plastic shrinkage crack. If you ignore her altogether, she'll give you more of these. Now this isn't the concrete mixture's fault. It's a result of poor conditions and poor coordination of placement, finishing, and curing the concrete. With those conditions, the placement of the concrete was delayed until we had more favorable conditions seen here. These were the conditions for the I-40 Belmont Bridge project, which was an accelerated bridge construction project where the new bridge was constructed alongside the old one demolished, and the new one slid into place. With the silica fume bridge, we didn't experience a single crack in the deck. We had similar conditions for the McConnell Bridge, which is located at the north end of I-17, actually State Route 89A, just as you're coming into Flagstaff. So here's a picture of the McConnell Bridge, the first phase. This is the northbound side. And here is an additional picture of the second phase. It's in process with the curing compound being applied. And then here's a nice picture looking north at the second phase with the San Francisco peaks off in the background. And they're still applying the liquid membrane forming curing compound to protect the concrete while it's still in the plastic state. And the white rolls are the curing mats that get pre-wetted prior to rolling out over the concrete after the concrete has set up sufficiently to not get marred while curing mats are being placed. So let's back up a bit to concrete protection. This is important while the concrete is still in its plastic state and before the wet curing process has begun. So the first option is, of course, to wait for more favorable conditions based on weather and the concrete temperature. And with this, you can determine the evaporation rate either using ACI 308R or by using the nomograph that's included in both ACI and an ADOT specification. Concrete protection is required if the evaporation rate is greater than 0.10 pounds per square foot per hour. Protection could include fogging equipment and/or windscreens. The most essential item to consider, however, is to have a well-coordinated and well-executed placement without interruption, over or undersupply, as well as a sufficient number of workers to keep up with finishing and placing the curing mediums. Okay, back to some of the benefits of silica fume. So here is reference information for the effect of silica fume on compressive strength of concrete. Remember, ADOT typically uses about 4 to 5% silica fume at a water-cement ratio of 0.45 or less. These numbers are for concrete that does not include fly ash and is at higher water-cement ratios. We can see that between 5% and 10% silica fume will provide the greatest increase in compressive strength, and the higher water-cement ratio results in slightly reduced strength. So how does the silica fume increase the compressive strength of the concrete? Well, similar to how the fine aggregate fills in the spaces between the coarse aggregate, and the cement fills in the spaces between the fine aggregate, or sand, to form the paste, the silica fume fills in the spaces between the cement particles. Remember, JoJo mentioned that the silica fume is 2 orders of magnitude smaller in size than a typical cement particle. In the FHWA Silica Fume User's Manual, they draw the comparison in size to U and the Washington Monument. We refer to this as particle packing. Dr. Barzan Mobasher and his team of graduate students at Arizona State University have done some rather impressive work on particle packing in what we are referring to as ultra-high performance concrete, with additional cementitious materials producing strength in excess of 20 KSI. While that isn't needed for bridge decks as we currently reinforce them, the technology is being deployed, and at some point in the future we may see it appear on bridge decks, but nonetheless the principle of densifying the concrete through particle packing physically increases the strength, but there is a point of maximum return. But it isn't particle packing alone. It is also the chemical nature of the silica fume that improves the concrete strength. So in a nutshell, the silica fume both densifies the concrete and increases the number of particle bonds within the concrete, both of which increase the strength. We typically see about 5,900 psi in our standard Class S concrete mixtures on our bridge decks. The graphic combines all mixtures for bridge decks and may be a bit of an overstatement, but with inclusion of silica fume, we typically see at least a 9% increase or greater in strength, and we average over 8,000 psi with silica fume included in our bridge deck concrete. More than sufficient based on our design standards, but the strength increase is realized because of the effort to reduce permeability. And what do we mean by permeability? We mean the ability of the water, and more specifically, dissolved chloride ions within the water, to penetrate through the concrete. So how do these chloride ions get into the regular concrete? Where do they go and what do they do? Remember, JoJo mentioned that excess water in the mix, after having been placed, is displaced by the more dense aggregate and cement. As the water moves toward the surface, it forms capillaries within the concrete, some of which remain in place even after the concrete is hydrated. So 2 things have happened. The first is water has made its way to the surface, which, if worked into the surface by the finishers, will drastically increase the water-cement ratio at the surface, and within 1 winter, the surface will begin to delaminate or spall, as is what happened here. The second, not only is the integrity of the surfaces compromised, but the capillaries provide a clear path for water and salts to penetrate the concrete. Third, The concrete simply is not as dense, so it is therefore more permeable without inclusion of the silica fume. So if we are not in the very low range, 1,000 coulombs or less, then these damaging effects are more likely to occur. We can have leaching of the calcium hydroxide from the paste, decalcification of calcium silicate hydrate, those are the CSH bonds that provide strength, conversion of CSH to magnesium silicate hydrate, or MSH, formation of salt crystals, formation of oxychlorides, acceleration of alkali silica reaction, ASR, and alkali carbonate reaction, ACR, and also corrosion of the reinforcing steel. If you're looking at the photo and you're thinking, that looks a bit too green to be here in Arizona, you're correct. The photo is of a bridge barrier up in Michigan. To illustrate how the damage is occurring, the Michigan DOT included this photo in their report, referenced here. If you're fascinated by this phenomenon, I recommend report number UT 13.09 by Simsian and Guthrie out of Brigham Young University, referenced here. You might also look up some of the work by Jason Weiss. So let's recap. Water plus freeze-thaw plus de-icing chemicals is bad. And not just for the bridges that see the snow and direct application of the de-icing salts, but also the bridges down the road, and that is why we're using the silica fume concrete on I-15 in the Virgin River Gorge. Not because it snows and freezes regularly, but because the de-icing salts get tracked out of the snowy regions of Utah all the way down through the gorge. If we compare the chloride permeability of our typical Class S mixtures to those with silica fume, the reduction is quite apparent. Here we have mixtures produced with 3 different aggregate sources, and you can see the reduction in permeability from the low to moderate range to very low, except for source C, from which a silica fume mix has not yet been produced for ADOT. Also of note for durability is the air void system. Notice the scale of 0.5 millimeter. These are not coarse aggregate in the photo. These are very small granules of sand. Notice the relative size and distribution of the air bubbles. This is a characteristic of durable air-entrained concrete by ACI recommendations. So in this photo, you see lots and lots of air bubbles. It's the same scale as the previous image, but what do you think about this concrete? Is it durable? Probably. Does it have adequate strength? If you said no to having adequate strength, you're correct. This particular sample proved to be far too many air bubbles placed too close together, which compromised the strength of the concrete. It turns out that as we are adding additional supplementary cementitious materials such as fly ash, including 20%, and silica fume, included at what percent? Yep, about 5%. By densifying the mixture, we are decreasing the permeability by such an extent that the hardened air void properties may be less vital to achieving freeze-thaw durability. Now, do not go and eliminate air entrainment for your higher strength mixtures subject to freezing conditions, but in areas where saturation over extended periods of time is less likely to occur, and the concrete is enhanced with materials such as fly ash and silica fume, you might do a bit of testing or research to test how well the mixtures might perform with a reduced entrained air content. But for now, approximately 9% in the paste is a magic number based on ACI recommendations. And by paste, we are referring to the water, cementitious materials, and fine aggregate. So here are the general requirements for a silica fume concrete mixture that would be placed on one of ADOT's bridge decks. The mixture is somewhat prescribed but gives the suppliers room to develop a suitable mix with the materials they have available. Much of this will be governed by the aggregate source, the nominal maximum aggregate size of the aggregate, and the initial water demand to create a viable mix that can then be adjusted with water-reducing admixtures to get the desired workability. Notice the total cementitious material is limited based on aggregate size. The smaller the aggregate, the greater the water demand, which requires additional cement to maintain the water-cement ratio in strength, which increases paste content, which is where shrinkage occurs. We limit shrinkage to 0.04%. Here are some of the specific challenges related to use of silica fume concrete. Some of this can be related to a steep learning curve, and as usage becomes more common, some of these challenges will become less significant. If there's any contractors or concrete subs that are viewing the presentation, please join in the chat and express some of the challenges you've encountered or that you might be concerned about, and feel free to express the same during the question and answer session following the presentation. So to help facilitate placement of the silica fume concrete, we developed 601 SF deck, which is ADOT stored specification, and we included a few different requirements in it, in addition to what we talked about with the mix design. So for preparation, we talk about a field demonstration to make sure all of the equipment and materials are coordinated. For placement, we try to limit the placement to within 10 feet of the screed. We try to limit hand tooling for finishing the concrete. And we also talked about windscreens and fogging equipment to try to reduce evaporation. For curing, we extended the length of the curing from 7 days to 10 days for the water cure. And in general, all of these requirements, they're not so much related to the materials themselves, but to the quality of the construction and the workmanship. And this was really a joint partnership between ADOT, industry, and academia. ASU played a big part in the effort, as did some of the local experts here in the Valley, different materials testing companies, and especially the ready-mix concrete suppliers, the cement industry, and also the chemical admixture industry. So it was a big effort, took several years to accomplish, and we hope that we're going to get better performance out of our bridge decks because of it. So to talk about some of the costs associated with it, I'm going to hand this back over to JoJo.
Thank you, Nye. Very well examined and discussed. So now on to the cost analysis. So cost information was obtained for 10 bridge decks that were recently constructed in the northern area of Arizona using conventional Portland cement concrete. The combined cost of the structural slab and overlay were then compared to the cost of Virgin River number 4 with a full depth silica fume bridge deck. So these tables give the individual and average costs of the two different deck systems. And as we can see here, the cost of the full depth silica fume deck is about 10% lower than the combined average cost of the structural slabs with normal Portland cement concrete. It was actually expected that the silica fume concrete would be slightly higher in cost due to the typically higher cost of silica fume compared to cement. Also, the limited number of full depth silica fume decks that have been placed in the state of Arizona, and also the need to adapt various construction procedures for its placement. But the lower cost of silica fume also provides an added benefit towards its use in bridge decks. And while the initial costs indicate a savings by using full depth silica fume, it should not be the overall deciding factor in their use. It's still necessary to ensure that they can be consistently constructed properly and able to operate at a level of performance equal to or greater than that of the current overlay system. However, with proper construction and care, it's expected that the silica fume bridge decks can perform at a comparable level and most likely out at a higher level than the current deck systems. So the construction and testing of the silica fume bridge decks have identified some definite advantages towards the use of silica fume concrete. And the following lists are just some of the advantages identified with using silica fume in the placement of monolithic bridge decks. So reduces chloride permeability. This is one of the biggest advantages of using silica fume concrete, which is the refined pore structure of the mortar. As Nye mentioned, this dense matrix really reduces the ability of chloride ions to penetrate the concrete and corrode the reinforcing steel. Also, shortened construction time. So by placing a monolithic deck, construction time is reduced by approximately 1 week. And this reduction in construction time then allows for the placement of bridge decks later in the construction season. Reduce costs. So the cost analysis performed show that the placement of the full depth silica fume bridge deck was approximately 10% lower than the placement of conventional concrete. And actually, when research was being done in the Minneapolis and St. Paul metropolitan area, their cost analysis actually resulted in a 15% reduction in price for silica fume. So we are really seeing some impressive results throughout the country. And then compressive strength. The mixes containing silica fume had slightly higher compressive strengths than similar concrete mixes without silica fume. So limited long-term strength data has shown compressive strengths of 9,000 psi after 1 year of concrete containing silica fume. So the performance of a few of the bridge decks, however, should also raise some concern and be addressed to prevent the development of future problems. So some of the concerns raised regarding the use of silica fume included the development of silica fume balls at the surface of the bridge deck that could cause spalling and pop-outs, development of shrinkage cracks on the bridge deck surface due to surface drying, and the ability to maintain a moist environment over the bridge deck surface. The workability of concrete is also an important parameter in the design of the concrete mix proportion. Silica fume concrete is not easy to make the concrete vibrating close-grained, which can influence the smoothness of concrete quality and uniformity of the surface. But again, these problems can be easily solved by changes to some of the current procedures and should not inhibit the continued placement of full-depth silica fume bridge decks. So from the results, it is concluded that the silica fume is a better replacement of cement. The rate of strength gain in silica fume concrete is very high, and after performing all the tests and analyzing their results, these following conclusions can be derived. So with the increase in water-cement ratio, strength of concrete decreases. The optimum value of compressive strength can be achieved in 10% replacement of silica fume. Workability of concrete decreases as increase with percent of silica fume. And compressive strength decreases when the cement replacement is above 15% of silica fume. So based on the results obtained from this study and the successful completion of the full-depth silica fume bridge deck, Virgin River number 4, the following recommendations were made. Continue to implement the use of full-depth silica fume bridge decks. It is recommended that this implementation continue to be gradual to allow contractors, inspectors, and concrete plant operators to become more comfortable with the construction processes and adapt their construction procedures. This will also allow for the continued refinement of current specifications as problems arise, as well as allow for continued monitoring of the performance of silica fume decks. And also monitor the air contents of future projects to determine the variability of the air content due to pumping. It's recommended that air contents be measured before and after pumping the concrete to determine the amount of air that is lost and to ensure that an adequate hardened air void system and durable concrete is obtained. That was the end of our presentation. If you have any questions or concerns, please feel free to contact us through the chat or email either myself or Nye McCarty. And thank you very much.